Hello, my name is Tiago. I'm a Ph.D. candidate in information technologies. Marco is the advisor, and Manuel Iori is the co-advisor of this work. In addition, Mairo Moreira and José Fernando also collaborated with this project. Our work is named Algorithm for Cutting and Packing Problems. We've addressed two main problems, so I divided my talk into two main parts. The first one is related to the pallet building problem, and the second one to the rectangular cutting problem. For each part, I will discuss these topics. Okay? Let's start with pallet building problem. To start with, what's the proposal? Well, this proposal arose from a real-world application subject to non-trivial constraints, and the idea came from Elettricotanta, an Italian company for automation of production processes. I highlight that we don't have a partnership with this company. They only gave us their database to develop our research. Well, about the processes, they consider several ones, but our interest is in picking and packing. What is this? This is the task of creating pallets from individual 3D items. This problem is also called distributor pallet loading, where a pallet is composed of boxes from different customers, because in general, a single customer cannot afford the whole pallet. It's required a packing that speeds up load-unload operations, right? And how to build a pallet? Let me give you an example. A pallet has a base and it's created by placing boxes on there until it's filled up. We also could create a pallet with different boxes in this way, for example, but which one would be the best? Good question. In most cases, we don't know the answer. However, we have the conditions to create it, which are all items should be placed on a pallet in such a way that the constraints are fulfilled and the number of pallets used should be as low as possible. So the key is to understand the constraints of the problem, right? So let's do that. The first constraints regard the basic ones. We address three of them. No overlap, items limited by space and rotations. We also address more complex constraints, fill factor, related to the required utilization percentage of a specific surface. These cups, for example, represent different fill factors. And the stackability related to the item disposition on pallets, which restricts how the boxes can be placed on top of each other. And practical constraints. But before presenting them, I explain the family concept to separate items. Family is the generalization of a concept. Practical example, the glass family here. While type is its specification. For example, mugs, cups, wine cups, objects made of glass. Okay, but why is this concept important? There are several reasons. First, it allows to divide the pallet in smaller parts by using layer levels with items of the same family. This pallet, for example, is composed by 3 levels. This division simplifies the algorithm to create pallets. But why do we place items of the same family on the same layer? Because it emulates the stability constraints. Since items of the same family have similar height and weight, not necessarily equal, but very similar. So to avoid this situation, unstable pallet, layers composed by those items tend to create stable pallets like this one. All right? So based on the layers composition, we classify them into types. First, single item layer composed by items of the same type, which is represented by a color in this figure. Next, single family layer composed by items of the same family but different types. And an exception here. Each pallet may have a layer composed by multiple families, but only one layer with this composition. And this layer is called residual layer. That said, the family concept defines the layers disposition. First, items of the same type must be contiguous. Second, at least one item of a group must be visible from the border. I'll give you an example. Considering these figures, the first two meet both requirements, as we can check. On the other hand, the last two fail to meet at least one of them, right? Finally, the types of layers define the pallet disposition. The first part is formed by the most stable layers, the single item layers. Next, layers composed by different types but the same family, the single family layers. Last, one layer to close the pallet, the special residual layer. Okay? To solve problems related to PPP, the literature presents several approaches. This serving board presents a collection of the state-of-the-art packing strategies. It's very common to use constructive approaches. For example, this paper in which we base our algorithms. A two-step strategy to create solutions is frequently applied for both the exact and heuristic algorithms. Regarding heuristic to 3D items, the two-step approach proposed in this paper is the closest to ours. However, the goal of all present papers is only optimizing the fill factor of pallets. Therefore, propose to go beyond that goal by meeting the contiguity and visibility constraints. To achieve this, we propose four main strategies, these ones, and all of them use the two-step heuristic to create a solution, creating first layers and then pallets. Now I will go into detail for each of them. The first one is our base heuristic algorithm called EPMH, which is an adaptation of the extreme points heuristic with evaluation functions to create layers and a grid heuristic for generate pallets. I highlight that this heuristic is deterministic and has no local search methods. In details, first, extreme points heuristic. Give an item, K for example, and a partial solution, we should pack K. To do that, we use one of the feasible points called extreme points. So I select one of them and place the item there. Then remove this point and new extreme points show up. The set of extreme points is updated by adding the blue points. In the next iteration, all these points will be considered. However, which extreme point should I choose since the algorithm must meet the practical constraints? So we adapted this heuristic to analyze points. For example, to meet the visibility constraints, we must place K in such a way it touches the border. So given all these extreme points, only the black point should be visible. Okay, that's it. The same goes for the contiguity analysis, and the set of points is updated, right? Now given feasible extreme points, which one is the most suitable? So we use metrics to evaluate each of them when placing the item in that point. And we've implemented this list of metrics. That's it. And the grid heuristic to generate pallets that stacks layers. So it starts from the top by inserting one residual layer, then as many single item layers as possible. Finally, if there's still room on it, as many single family layers as possible. Regarding the results, I would like to draw your attention to the bounding box function here, which shows significantly better results than the other metrics on 24 real instances. Regarding the second proposal, we've included in it the grasp meta heuristic. Now, grasp is the previous grid heuristic to create pallets, and the extreme point heuristic with reactive grasp for creating layers. Its improvement phase is based on an upper bound heuristic that is included in the graph framework here in order to launch the improvement phase. Additionally, the algorithm updates the reactive structures at the end of each iteration. Regarding the reactive method, it's a probabilistic and dynamic method to select a function that will evaluate an extreme point. For example, given 3 fitness evaluation functions, in the beginning the probability to select a function is equal for each of them. However, during the iteration, these probabilities will change. Suppose this scenario at the iteration 1000, so f1 here has higher probability to be chosen, right? When analyzing the results for pallet and layers, although the number of layers in graph is greater than the first proposed solution here, the number of pallets is lower than the first heuristic. This indicates that the composition of pallets is important. Considering the last analysis, we proposed the third solution, an EPMH, an algorithm without an improvement phase, composed by a mixed approach which uses a heuristic for creating layers and an exact algorithm for building pallets. So basically, this exact algorithm stacks layers by meeting the pallet constraints with an objective function which minimizes the number of pallets. In addition, we tested 3 different values when considering not an exact but a minimum value of fill factor. These are some of the results of the third proposal. The improvement was greater than 8% when considering a minimum fill factor value equal to 55%. Finally, we proposed, from the best of our knowledge, the first mathematical description for this problem. Additionally, we've proposed new math heuristics based on heuristic and mathematical models. Regarding the math heuristic, its mathematical model is a method for a knapsack problem. However, instead of considering the whole set of items, that method optimizes a subset of items. So, we have a solution created very fast through a heuristic, then the model will re-optimize it considering only one more item. Okay? Regarding the mathematical model, a brief explanation of the constraints proposed. First, these constraints are applied for verifying overlap among items. Next, the contiguity is met through these constraints. Additionally, we must ensure that items of the same types are connected, otherwise multiple contiguous groups could be created. Next, the visibility is also met. And finally, its objective function considers the bounding box of the items packet because it favors compact arrangement of items. For example, considering these 2 different packings, the bounding box of the second case has the lowest perimeter, so this is the optimal solution. I present the last result for PBP, a comparison for the number of pallets. In this case, GraphFull here outperformed all other algorithms. When it comes to time consumption, GraphFull is the most time consuming. However, this increase in time is worth it. I show you some conclusion for this first part. First, the mathematical formulation proposed is an important contribution for the literature. Considering parametric configurations for heuristics, the most important are the bounding box as evaluation function, as well as a lower fill factor to improve the quality of the solution. Although the combination of heuristic and mathematical models in the math heuristics improves the algorithm effectiveness, it's difficult to find a fine parametric configuration that generalizes its use. When it comes to future works, we have the following. To improve performance, the proposals include innate learning mechanisms to select items, as for example, support vector machine. Building blocks is an efficient, exact method to pack similar items, so we may take advantage of it when creating single item layers. Finally, we propose to combine different problems, for example, packing and delivery, to try to improve the logistic of the whole process. Okay, so the second part of this presentation is related to the rectangular cutting problem. First, the proposal is to develop a flexible mill for the two-dimensional cutting and packing problems that considers both the guillotine and first-order non-guillotine cuts. To this end, the proposal is based on the innovative idea of floating cuts, a technique that simplifies the regular mill models. For example, the number of variables is reduced since it does include variables related to the coordinates of the items. Regarding guillotine and non-guillotine cut types, how to define them? It's simple. Considering any two-dimensional plate, guillotine cut means that it's always possible to cut from an orthogonal edge to the opposite one. On the other hand, non-guillotine cut means that it's not always possible to do that, as this case. Regarding floating cuts, we don't have X and Y coordinates of the items as regular mill models consider. Instead, we assume that from a given plate, a maximum number of new plates can be obtained without explicitly identifying their dimensions. So, a decision variable is associated with a cut and not to the position of the cut, as shown here in the figure. And the position of an item is based on this division here. Regarding the constraints, we address only the basic ones as we did previously. We base this proposal on the following works. Surveys, the previous ones are useful also here, and we've considered this one to address knapsack problems. When it comes to models to solve this problem, the research method was first proposed by Christofield and Whitlock to solve guillotine cuts. Relate to non-guillotine cuts refer to FICAT. Dynamic programming is an efficient procedure to reduce the search space and avoiding redundant solutions. Constraint programming was used for both the guillotine and non-guillotine cuts. Additionally, pseudo-polynomial mill models were proposed in the literature. Finally, heuristics were also proposed to solve the RCP problem classes. However, neither one is flexible enough to address both the guillotine and non-guillotine cuts. So, to cover this requirement, we propose a general and flexible parametric mill model to address both cut types. According to Washer, rectangular cutting problem, or RCP, is a generic cutting problem which may be divided in many classes. Our work addresses two of them: single large object placement problem, or SLOP, and single knapsack problem, or SKP. So, the proposal is to create a flexible model to solve these RCP classes by covering these specific variants. To solve the problem with no guillotine cuts, we propose the 5 arcs model. It's called so because this type of cut is based on the first order no guillotine pattern, in which an item is composed of 5 pieces: top left, top right, bottom right, bottom left, and center. This is the pattern of this cut type. So, based on that idea, each piece is represented by a node in a tree where the root is the original plate. Since this is a recursive structure, the division for each piece continues for a predefined number of times. That's why this is a parametric model. When it comes to guillotine cuts, we propose an extension from the 5-arcs model. The idea is similar, however, we cut a plate in at most 4 pieces. This is done by considering 2 possibilities for cutting it vertically, then creating the pieces left and right, or horizontally, then creating top and bottom pieces, right? The tree is similar, however, each node has only 4 children. In addition to that, we proposed several valid inequality constraints to strengthen the model. I present only the symmetry reduction for the 5-arcs model. When we refer to a symmetric solution, we mean the exact same solution from another perspective. For example, this is a non-guillotine solution, but rotating it, we have the same solution. Similarly, mirroring it, we have another perspective. Finally, applying another rotation, again, the same solution. So, the model must allow only one, and the constraints proposed cut 3 of them, strongly reducing the search space. Now we focus on the results. We've run extensive computational experiments to assess the model's performance when considering constraints to strengthen them. I highlight the results considering the non-guillotine model in this figure when addressing both classes, SKP and SLOP, in which the constraints included strengthened the base model here, both cases, with a large positive impact on the solver gaps. Furthermore, we analyzed the model's performance in comparison to the state-of-the-art formulations in the literature. When it comes to SKP, the model proposed to guillotine cuts outperformed the literature approaches when solving 24 instances optimally here instead of 21. However, when it comes to SLOP, the number of optimal solutions found was lower, 27, comparison to 47, although the average for the optimal gap is still low here, about 2%, which is not the case when we analyze the gap in the literature for the SKP greater than 12%. Well, our conclusion for this second part are the following. Floating cuts technique can be used effectively to provide several benefits, among them the flexibility. As we've seen, flexibility is the main point of this model, being applied to several problem variations and additionally being very competitive in most cases. Regarding future work, some suggestions. Improving upper bound by adding new valid inequality is the most basic idea, although it's a very difficult task to accomplish. Additionally, to propose new branching price algorithm for cutting packing problems, since the classes addressed arise as price problems embedded in the column generation procedures to solve the bin packing cut stock, for example, meaning that this new MILP can also be used in the resolution of these problems. Regarding the PVP publications, we've published 3 papers on conference and a paper in a journal. Regarding the RCP, we submitted a paper to a journal. To summarize, we've proposed several contributions for cutting packing problems, but even more importantly, these approaches are new ways of looking at these problems, which could serve as a catalyst to even better approaches. And this brings us to the end of this presentation. Thank you for your attention.